5.2 kind of puts together two concepts that we dealt with in 5.1. Z-scores and areas or probability of Z being in particular regions. Now, the reason we convert things to Z-scores is there are lots and lots and lots of normal distributions. Some normal distributions are wide, some normal distributions are narrower. Some normal distributions might have a mean of 200, where another normal distribution might have a mean of 280,000. But they have one thing in common in that they're all normal distributions. And instead of having to have a separate table for every possible normal distribution, we standardize things. We convert things into Z values, so we refer to things in terms of their distance from the mean in terms of their standard deviation. So let's work through an example to see what we mean. So let's say for some random variable, that population has a mean of 81 and a standard deviation of 5. And we know that this is a normal distribution. So in terms of our x values, our mean 81 is in the middle, and then this describes kind of how wide it is. So let's convert those into Z values. So remember that in terms of Z, 81 is at the mean, so it is 0 standard deviations away. So our question is, what is the probability of selecting an x value that's less than 76? So we have some distribution that has an average of 81, this standard deviation. How likely is it that we select a single element, one element that falls in the region of 76 or below? Technically just below 76. So what is the likelihood of being in that region? Well, our table doesn't deal with averages of 81s and standard deviations of 5, so we have to convert those into Z values. So let's find out what is the Z value that corresponds to 76. So we take our x value and we subtract the mean, and we divide that by our standard deviation. So 76 minus 81, that's negative 5, divided by 5. So 76 is one standard deviation to the left of the mean. So by asking what is the probability that x is less than 76, that's equivalent to saying what is the probability that z is less than negative 1. Those are comparable statements. So if we can find the area to the left of z equals negative 1, we can find the area to the left of x equals 76, which is that probability of being in that region. So if we go to our table, let's see, do they have that table handy for us? We may have to look it up in the book. So since they don't give us a quick link to the table, if we go to the ebook, we'll go to the e-text, and the table of contents are on the left. If you go down to the table of contents to the very end and select appendices, Appendix B is tables, and it turns out on page A16, Table 4 of Appendix B, is our table that we've been dealing with. So we were going to look up a z-value of -1. So if we go down to a z-value of -1, here's -1.0, and we need -1.00. So this top one is the 0, 0. So -1.00 is right here, 0.1587. So that's the area of that region, which corresponds to the probability that z is less than -1 or that x is less than 76. So if our distribution is normal with this particular average and this particular spread, 15.8% of the data falls in that area. So if I'm randomly selecting an element out of the population, I have a 15.8% chance of selecting an area that is, or an item that is less than 76. So let's continue on to another one. This one has 2 pieces, so let's find the probability of selecting a piece of data that is between 78 and 86. So what is the probability that our data value is between 78 and 86, but we need to know more information. The mean of our distribution, our normal distribution, the mean is 90, and the standard deviation is 4. Now this only works because we're told that this is a normal distribution. If it was not a normal distribution, if it was a skewed distribution, then we couldn't follow this process. So this might be a test where the average for this test is 90 with a standard deviation of 4, and we want to find out what is the likelihood that someone scores between 78 and 86 on this test. So the mean, in terms of x, the mean is 90. We want to find out how likely is it that someone scores between 78, which is to the left of the mean, and 86, which is also to the left of the mean. So we want to find this area, which corresponds to the likelihood of this event. So we need to convert each of those into z-values. So let's find what is the z-value associated with 78. So we need to find out how far is 78 from the mean. So our x value minus the mean, and then convert that into the number of standard deviations. So 78 divided by 90, that's -12 over 4. So that z-value is -3. And then let's look at the z-value for 86. So how far is 86 from the mean? And then how many standard deviations is that? Remember, we're using 90 and 4 because that's the mean and the standard deviation for our particular distribution. So 86 minus 90, 86 is 4 units below average. 4 units, that's 1 standard deviation. Notice 4 divided by 4 is 1, and it's below the mean, so -1. So an equivalent statement would be, what is the probability that z is between -3 and -1? This is the values for our precise population, our problem, but in terms of standard values or standardized values, it corresponds to this. So we need to look up -3 and -1 in our table. So if we go to our table and go to -3, -3.00.0013. So this area here is 0.0013. That's everything to the left of that. Now if we look up -1, that is all of the area inside there, which is too much. That's more than what we need. So if we look up -1, -1.00 is 0.1587. So that includes too much. So we're going to take that 0.1587 and say, well, we don't want to include this part. This is how much too much we are. So we're going to take that part away. And whatever we're left will be that area. So 0.1574. So that's the area in between these two. So in other words, the probability that our value is between 78 and 86 is 0.1574, or about 15.74%. So if this is the average for a test and this is the standard deviation, you have about a 16% chance of making somewhere in this interval for your test grade. So let's go on and do a word problem. Let's look at this one. The amounts of time per workout an athlete uses a stair climber are normally distributed. So if we can look at different times for people using the stair climber, it's a normal distribution. There are a few people that barely use the stair climber at all or almost none. There are some people that use the stair climber excessively, but people tend to average around somewhere in here. So we're told that the average time, the mean time on the stair climber is 20 minutes. And the standard deviation of times is 5 minutes. So they give us several scenarios. Find the probability that a randomly selected athlete uses a stair climber for A, less than 16 minutes. So what is the probability that the person selected uses the stair climber for less than 16 minutes? So let's just make a note. X is our random variable. X is the number of minutes a person uses the stair climber. So it's the number of minutes the person uses the stair climber. So if I randomly pick a person, what is the likelihood that the number of minutes is less than 16? So that's an X value. So remember, for our distribution, the mean is 20. So 16 would be over here somewhere. And we want to find the probability that the person uses the stair climber for less than 16 minutes. For less than 16. So we need to convert that into Z. So the Z value associated with 16 is 16 minus the mean divided by the standard deviation. So 16 minus 20 over 5, so -0.8. So that's how many standard deviations below the mean 16 is. So we're wanting to find the probability that Z is less than negative 0.8, which corresponds to the probability that the minutes used is less than 16. So if we look up negative 0.8 in our table, negative 0.8, and we don't have a digit past that, so 0, we get 0.2119. 0.2119. That's the area to the left here, which corresponds to the the probability. So the likelihood that someone uses the stair climber for under 16 minutes is a little over 21%. A little over 21% of the time we will select a person that uses the stair climber for under 16 minutes. Now we could do the same thing for the other scenarios. We could find out what is the likelihood that if we select a person that uses the stair climber between 20 and 27 minutes or for more than 30 minutes. We would just want to draw our distribution. We would want to list the X value or X values given to us and find the included area. Let's finish up working one more. Let's work number 8. It said use the normal distribution of SAT critical reading scores for which the mean is 513. So our mean is 513 and our standard deviation is 121. Assume the variable X is normally distributed. So X is a normal distribution. What percent of the SAT verbal scores are less than 675? So if X stands for SAT scores on the verbal section, we want to find what is the probability that if we select a person that their verbal SAT score is less than 675. So let's draw our distribution. It's a normal distribution. The mean is 513. That's in terms of X. So we want to find out what is the probability that someone makes 675, actually not 675, but less than 675. So 675, that's more than the mean. So we want to find out how many people or what percent of people make less than 675. So we need to convert that to a Z value. So what Z corresponds to 675? So take our data value minus the mean divided by the standard deviation. So X minus the mean over the standard deviation. So 675 minus 513, 162. Divide that by 121. That's 0.1, let's call that 1.34. So that is the Z value that corresponds to 675. Now we want to find out what is our area in there. So if we pull out the table, we need the table with positive Z values, so here. So 1.3 is here. Here's the 04 column, so here's where 1.34 comes together, 0.9099. 0.9099. So in other words, 90.99% of the population make less than 675 on the verbal part of the SAT. This is the portion or the proportion of people that make less than 675 on that test. So that's what the first part of the question is asking. what percent of scores are less than 675? The second part says, if 1,000 SAT verbal scores are randomly selected, how many would you expect to be greater than 550? So we don't have 550 on this one, so let's erase and let's redraw our chart. We still have the same distribution. It's still a normal distribution with a mean of 513 and a standard deviation of 121. This time we want to find out of 1,000 people, how many will score greater than 550? So 550 would be over here. If we want to know how many people, first we need to know how likely is it for someone to be in that area. So what is the probability that a single person scores more than 550? Or you can say, what percentage of the population scores more than 550? So we need to convert those into z-values. So if we find a z-value for 550, that's 550 minus the mean over the standard deviation. So 550 minus the mean divided by the standard deviation. So 0.31. That's not the proportion, that's just the z-value. So we want to find out, well, what is this area? Well, if we look up 0.31, we're going to get this area. So let's do that. If we go to our table and look up 0.31, the area to the left of 0.31 is 0.6217. We want the other portion, so the complement. So remember, this probability is equivalent to the probability that z is more than 0.31. It's the complement of that area, so 1 minus 0.6217. So this probability, 1 minus 0.6217, 0.3783. So that's the portion of people that score more than 550 on this test. So we need to find out, well, what does that have to do with what we're being asked? We're told that we're taking a sample of 1,000 people, and we're essentially looking for 37.83% of that 1,000 people. If this is the proportion of people that fall in that category, then how many people out of 1,000 will fit that? So what is 37.83% of 1,000? Or what is 0.3783 times 1,000? Remember, when we're multiplying, we like to leave it in decimal form instead of percent. Of means multiply. So if we multiply that out, 37.83% of 1,000 is 378.3. So about 378 people would be expected to score more than 550 if we took a sample of 1,000.